All right, AP Chemistry students, here we go. So it is Monday at 3:30 of Snowmageddon. Our gas molecules outside are decidedly lacking kinetic energy, which is a really, really nerdy way of saying it's really cold outside, okay? Anyway, so we'll get into thermodynamics later. All right, so here's normally what happens is that after this buffer assignment, we start into this lab. But because of any number of factors, number one, tomorrow being Tuesday, and we're going to be remote learning, this is why I'm doing this, and the fact that Wednesday's parent-teacher conferences, which is going to screw things up even more, so we're going to start the lab and do that like Thursday and Friday. I'll talk more about this later, but in an ideal world, everybody would be here, so if you could come in on, so if you're here on Thursday, it's not a big deal, but if you're like on a Friday group, if you could come in to do the lab and then reverse that on Friday, that would be cool. That way you can see the lab, we can get it all done. Anyway, something to think about. All right, and my phone just went off, so sorry about that. Okay, put that on mute. All right, so it's been a day. All right, so let me kind of go over some answers on what you should see on that big bad buffer assignment. So your answer to number one should be around 5. On number 2, every numeric answer on 2, A, C, and E, every one of those answers, this is an ish, should be around 4.5. Okay, now I want to make sure that we start this right. So like you've got 20 grams of acetic acid. You got to change that into moles, and this is going to be, because if this is wrong, everything else is going to be wrong. So when you change that into moles, that's 0.333 moles of acetic acid. And then you divide that by the 2 liters, that's 0.167 in terms of that molarity, okay? And then on your sodium acetate, you got 20 grams of that. That's going to be 0.244 moles, which is going to be 0.122 with the molarity. Because if those numbers are wrong, the entire problem is wrong, okay? So here's what you've got. Here's the molarity of those 2 liters of your acetic acid. Here's the molarity of the sodium acetate, because that's going to be a buffered solution. Okay, when you get to number 3 and you have to figure out the moles of that NaBr that you got to have, that answer is going to be around 0.2 moles. Okay, the easiest thing to do there is start with that Henderson-Hasselbalch, going pH equals your pKa plus the log of your anions divided by your acid, okay? And then solve for the concentration of those anions, okay? That's the easiest way to do that problem. You could also go, if you really wanted to, you could go Ka equals H times BRO divided by the concentration of HBRO, okay? You could do this and go from there and solve for the concentration of your BRO that way, if you wanted to do that, because you know the Ka, you know the pH, so you can find the concentration of your hydronium ions by taking the negative log of that. Okay, on number 4, let's talk about that one. This is comparing that weak acid to a strong acid. Here's the one that's missed most often. Is going to be B. If you look at that, MAVA equals MVBB, the moles of your acid needed is going to equal to the moles of the base needed. That calculation is not dependent upon whether it's a weak acid or a strong acid. You have the same number of moles of acid to neutralize as you need moles of base to neutralize it. Okay, so don't tell me, oh, the weak acid needs less or the strong acid needs more. It's a function of the fact that if you look at that equation, at the end of the day, it's some acid reacting with hydroxide to get water and that salt. So if you have 10 millimoles of acid, it's going to take you 10 millimoles of base to neutralize it no matter what. Okay? So there's that. On number 5, that range of answers should go from around 1 up to around 11. Okay, so that first answer on number 5 is going to start around 1, going to end up around 11. When you get to number 6, those answers are going to go from around 4 to around 10. And on number 7, those answers are going to go from around 8 to around 11. Okay, so that's just going to give you some ballparks on that one. When you get to number 9, both of those answers are going to be around 7.5. Okay, that's an ish, but they're going to be around 7.5. And when you get to number 10, when you're trying to figure out what those salts are going to do, so let's look at, for example, that potassium bromide. Okay, so if you take potassium bromide and you put that in water, you have potassium and you have bromide ions. Okay, that's what it's going to ionize into. Well, there's no way the potassium, the water, there's no way the potassium is going to give up a proton to the water and form H3O, and then that, okay, the proton is completely locked up in the nucleus of this potassium. There is no way you're going to get that proton out of there. Okay, it's not going to happen. Because if you did, it would literally take a nuclear reaction. You would have to overcome what's called the binding energy, which holds those nucleons together. Not going to happen. Okay, so no. Now the Br minus. Think about this. The Br minus is the conjugate base off of hydrobromic acid. That's a strong acid, which means that Br minus isn't going to react with water to form HBr and generate hydroxide ions. Okay, so if you add potassium bromide to a solution, nothing's going to change. All right. Now, if you contrast that with, let's say, for example, you have CH3, NH3Cl. Okay. And for the life of me, I can't remember the name of this molecule. Okay, let's not play name that molecule. I can't remember the name of it. But here's the point. This whole thing has a charge of 1 plus. The chloride has a charge of 1 minus. So this has the capacity to give up a proton. So this big complex ion here will, if you dissolve this stuff, will give up a proton to a water. You would drop this charge to being neutral, so this would be a CH3NH2. It would give up the proton to the water. That would be like what happened with you take NH4. NH4, you dissolve that in water, the pH goes down because you're generating ammonia and hydronium ions. So basically, if you look at this cation and it has an extra hydrogen, which is basically going to give up a proton, and it has a charge of 1 plus, it's going to donate that hydronium to the water. You're going to make H3O plus. The pH is going to drop like a rock. Okay, not like a rock, but it's going to go down. Okay, so what you should see on number 10 is that you should have 2 that have no change at all. You should have 2 that make the pH go up, and you have 1 that should make the pH go down. Okay? So when you get done with number 10, 2 will have no change, 2 will make the pH go up, 1 will make the pH go down. So that should get you a pretty good start. If anybody has any specific ones you want me to work on that, let me know. And like I preached to you on that first video, so help me, okay? So help me. Here's your sheet of paper. Here's this line. And for example, on like number 7, where you have A, B, C, and D, you do not stack these answers up here and then put this work down here. So help me, I am not going to grade your paper. 7A, boom, here's the answer. 7B, boom, here's the answer, there's the work. 7C, boom, here's your answer, there's the work. It's cold, I'm cranky, you keep me happy, okay? If you cannot follow these simple instructions, I swear to you, I don't care how right your answers are, I am not going to grade your paper, okay? You put your answer here, you put the work here, and you leave a space in between, okay? You leave a space in between these individual parts. If you have it, literally, go back and redo it, because I'm not going to grade your paper. If you're not sure if you're right, ask someone. Send a snap or send a picture to someone. Go, especially those that have had me before, which is most of you. Say, wow, is this going to make Burkamp angry? If that person says, redo it. Okay, if there is a moment of hesitation whether or not I'm going to be angry, redo that assignment. Okay. Now, so let's talk KSP and QSP. So you all have I'm going to send out these lecture notes. That's not what I want. Hold on. Give me a second. I'll stop this for a second while I send myself the right stuff. Okay, kids, sorry about that. I sent myself the wrong notes. All right, so this is what you all are going to have. This is notes on KSP and QSP. So as we go through this, and you just kind of follow along with these notes, if you can print them out before you continue on with this lecture. So here's the basic idea of what happens with KSP, and it's a similar type idea. So notice that we have K. So anytime you see the big K, that means the system is in equilibrium, okay? This is going to be important. The system is in equilibrium. So we're going to deal with KSP and QSP. So the SP stands for solubility product. So obviously this is a function of something being soluble or insoluble. So if you look in the back of your books, okay, on page 1093, okay? So on page 1093, you have a whole list of solubility products. Now, so like on all of these are pretty small numbers, like 10 to the negative 31st, it's like the really small ones. Some of them are 10 to the negative 8th. Some of them will be 10 to the negative 6th, okay? So, and this is what you see eventually, is that this has a similar concept of Ka values. All your Ka values are really, really small values. The same thing is going to happen with your KSP values. So here's what's important. You only have KSP values for things that are insoluble, okay? If things are soluble, you won't find this. So for example, you will never find the solubility or the KSP, solubility product of, say, for example, sodium nitrate. It's not here because sodium nitrate is very, very soluble. You only have these KSP values for things that are insoluble. Same thing is true like for Ka values. You never found Ka values for strong acids because they didn't exist because they were too big. Same thing is going to happen here. So you are not going to find KSP values for things that are soluble. You're only going to find things that are listed here for things that are considered to be insoluble. Okay, so that's going to be the difference. All right. Now, so we're going to look at a simple example of what can happen here. Okay, so let me scroll down here. And so I'm going to take some sodium nitrate, okay, NaOH, put that here in the beaker. Okay. Now, here's what's important. In this beaker, right here, okay, not a whole lot there. In this beaker, I have added sodium nitrate. Excuse me, sodium hydroxide. Sodium hydroxide is very, very soluble. It's a group 1 element. So what that means is floating within this solution are sodium ions and hydroxide ions, okay? They're bound up to water molecules, okay, but we just leave the water out of it. So here's what's important. These are existing as sodium ions and hydroxide ions, okay? They're not a chunk of sodium and a chunk of hydroxide, which doesn't make any sense anyway. But they're sodium ions and they're hydroxide ions. Now, to that, I'm going to add some magnesium nitrate, MgNO3. Now, if you're in Chem 1, you'd go, oh, sodium hydroxide and magnesium nitrate. Ooh, I can do this, okay? And you would go, oh, I recognize this. This is going to be a double displacement reaction. Cool. I can do this, Mr. Burkamp. I'm going to get sodium nitrate and magnesium hydroxide. Okay, it's a double displacement reaction. Magnesium is 2 plus, nitrate is 1 minus, sodium is 1 plus, nitrate is 1 minus. I get MgOH2. Oh, hey, I need to balance this. So I got 2 hydroxides, so I'll put a 2 over here. And now I got 2 sodiums, now I'll put a 2 there. And I got 2 nitrates, and I got 2 nitrates. Hey, I'm balanced. Wow, look at me. I can do chemistry. Okay? And you did. And in Chem 1, it was beautiful. Okay? But now I'm going to actually mix this up. So now I'm going to add the magnesium nitrate to it. Okay? When I do that, okay, it's one of my favorite words in chemistry. I am getting this gelatinous precipitate. Okay? So let me kind of, hopefully y'all can see this. Right? It's this chunky stuff. Okay? By the way, if you're in college and you let milk sit too long, this is what it looks like. If your milk looks like that, don't eat it. It's not cottage cheese. Throw it out. Just a word of advice. Okay. So something has formed a precipitate. So it's either the sodium nitrate or the magnesium hydroxide. That's it. Those are the only 2 things that can form a precipitate. So if you look on this handy dandy chart here, right, you'll notice that magnesium hydroxide has a KSP value of 1.8 times 10 to the negative 11. You will find no KSP values for sodium nitrate. You know why? Because it is soluble. Okay? You're not going to find one. So right away, I know my precipitate is magnesium hydroxide. So here's what's important. When I mix this up, I added magnesium ions to it, and I added a bunch of nitrate ions to it. Okay? That's what I mixed up. Okay? Those 2 things are what I mixed up. Now, at this point, it became like a dance. Okay? They're switching partners. So the magnesium comes along to the hydroxide and says, yo, sup? Hydroxide says, hello, sailor. Because the hydroxide is attracted to the sodium. Okay? They've been together. They've been sitting in this bottle for quite a while. Okay? So they've been together in this bottle for a long time. Right? So they've kind of hung out, but now the hydroxide comes along and says, oh, let me go over and see what's happening with the magnesium. Now, they become so attracted to each other. It's like love at first sight. They become so attracted to each other that they become so tightly bound that they form a precipitate. Okay? They're going to drop out of the solution. They're not going to be moving around anymore. It's like, hey, yo, I found my soulmate. And they're going to chill out. Okay? So it would be like all of you bouncing around inside this room. So imagine I'm going to bring the two groups of you together, right? Okay? And some of you are going to hook up and you go, wow, this is kind of cool, right? And you're going to form this precipitate, and you all are going to quit bouncing around, and you're going to sit together at a table. That's basically what happens when you form a precipitate. You have a cation and an anion that are so tightly bound together that they quit moving around and they settle out and they form a precipitate. So your net ionic equation is going to be Mg2 plus 2 hydroxide yielding MgOH2. Okay? Now, but that isn't the story. Okay? You're going to go, Bergkamp, this is a good story. Okay? The magnesium, they hooked up with the hydroxide. They made a precipitate. This is cool, right? It's a good story. It's right after Valentine's Day. Look, it's romance. No, that isn't the story. The story actually comes with what's happening in the solution above there. That's where the story is. Okay, and that's the most common misconception everybody has with KSP. So what happens is that I'm going to draw this big, okay? So here's the solution, and here's this chunk of magnesium hydroxide. Now, that's a solid. So what happens is that you still have some magnesium ions up here, and you still have some hydroxide ions. So here's the first thing I want you to get out of your minds right now. That when you form a precipitate, there are no ions in the solution above. Get that out of your minds right now. Stop. No. Get it out, right? Stop. Okay? There's still some ions up here. Not very many. Okay, and you'll see why in just a second. There's not very many of them. But there's going to be some up here, okay? Just not very many, okay? There's not very many ions. But listen to me. There are some ions up there. It's just a very small amount. So when I look at this, the story isn't the net ionic forming a precipitate. The story is the magnesium hydroxide trying to dissolve back into magnesium ions and 2 hydroxides. Okay, that's the story. So, and you're going to see this again and again and again. The reason that we focus on this is because it's always products over reactants when we calculate any number of things, okay? Products over reactants, and you all have seen that. If you look at HA turning into hydronium ions and anions, it's the products over the reactants, okay? So the same thing is going to happen here. So your KSP, just like Ka, so your KSP is going to be the concentration of my magnesium ions times the concentration of my hydroxide ions. Now, this is where this gets a little tricky, okay? If there's a 2 in front of this, like there is, that means that concentration is going to get squared. If there was a 3 here, if this was 3 hydroxides, this would get cubed. If there was a 2 in front of the magnesium, that magnesium ion concentration would get squared. So listen to me. Whatever values you have here for coefficients are what is what that concentration is going to get raised to. Okay? If there's a 3, there's a 3. If there's a 1, it's just to the first power, right? So this is why this magnesium is just raised to the first power. But the hydroxide, that's getting squared. Okay? Cool with that. Now, if it was like a 2 and a 3, this would get squared, this would get cubed. So whatever your coefficient is whatever you raise that exponent to. Okay? That is the most vital thing. Now, here's the big idea. So if you look at the KSP value for magnesium hydroxide, okay? Not manganese, but magnesium. If you look in your book, MgOH2 has a value of 1.8 times 10 to the negative 11. Now, again, here's this recurring theme of equilibrium. So what that means, here's what Mother Nature is trying to do. Mother Nature is going to get these concentrations here, whatever they are, multiplied together, And the concentration of that hydroxide is going to get squared. So Mother Nature is going to do whatever Mother Nature can do to keep these concentrations multiplied together to get 1.8 times 10 to the negative 11th. Okay? That's it. That's the magic number. That's when Mother Nature is in equilibrium. Okay, that's it. Now, here's the bigger idea. Just like Ka values, if this number is smaller, like let's say this had been 1.8 times 10 to the negative 21st, that would mean these values here would be even smaller numbers. If this Ksp value had been even bigger, like 1.8 times 10 to the negative 6th, these values would be larger, okay? Now, here's where Ksp differs from Ka. Notice that I don't divide by anything. And the reason that I don't divide by anything is because this is a precipitate, okay? Now, if it's Ka values, I divide by the concentration of the acid because I can talk about that concentration, okay? What's the molarity of the original form of the acid? I don't do that with this because this is a solid. So this is why you don't divide by anything, because this is what I said. You have to focus on making something be a precipitate, okay? So you're starting off as that precipitate, and then it's going to go into forming an ions, okay? But here's the bigger picture. Mother Nature is going to do whatever it has to do to get this value. Now, that's Ksp, okay? K is only when it's at equilibrium. Now we're going to talk about Qsp. Now, Qsp, the Q stands for quotient, solubility product. Mathematically is the exact same thing, okay? It's the exact same thing. You cannot tell a difference in the equations. Mathematically, it's the exact same thing. But your Qsp is a snapshot about what's happening in the system, okay? And you compare a Qsp to the Ksp, okay? This will make sense in just a second. So let's say, for example, that I mixed 5 milliliters of I'm just going to make up a number, of an 8-molar solution of magnesium nitrate, and I mixed 5 milliliters of a 0.6 molar solution of sodium hydroxide. Okay? That's what I did. Okay? I poured that. This is what y'all want to do in the lab eventually. I took 5 milliliters of this. I took 5 milliliters of this and mixed it together. Now, this is what I have to absolutely, completely stress to you. What the numbers that you plug in for this Qsp calculation, listen to me, listen to me, listen to me, have to be the concentrations after these things are mixed, not before, okay? These are the concentrations after they have been mixed, okay? Not once they're separated. This is the concentration after they've been mixed. So you can work with millimoles again. So if I take 5 times 0.8, I get 4 millimoles of magnesium nitrate. Okay? And if I take 5 times 0.6, I get 3 millimoles of my sodium hydroxide. Now, at this point, I'm going to divide by the total volume, okay? Because I need the molarity after they've been mixed, okay? So it's just like what you've done with acids and bases, and this is why I do acid-base first stuff before we do this, so you're used to this concept. Now, I'm going to divide this by the total volume of 10 milliliters, and I'm going to divide that by 10 milliliters. So I get 0.4 molar solution of my magnesium ions of MgNO3 and I get a 0.3 molar solution of my sodium hydroxide. Now, Again, I'm focused on the concentration of the ions that it's going to form this precipitate. So when magnesium nitrate ionizes, it turns into Mg2 plus 2 nitrates. Okay? Now, since the magnesium and the magnesium ions are in a 1-to-1 ratio, the concentration of my magnesium ions is also going to be 0.4. Now, technically the concentration of my nitrate ions is going to be twice that, which is going to be 0.8, but I don't care about the nitrate ions. That isn't the story. The only thing I have to worry about is the magnesium ions. But you do have to be careful. So if something dissolves in like 2-to-1 ratio, then that molarity is going to be twice that if that's the one that you have to use in the calculation. Okay, now my sodium hydroxide, that's just sodium ions and hydroxide ion, that's a 1-to-1 ratio, so the concentration of this is going to be 0.3. Now, I want you to notice something. And this works out well, mainly because of the fact that if you look at what I started with, notice that I started with a 0.8 molar solution of magnesium nitrate, but I end up with a 0.4 molar solution, okay? Now, notice that why that happens is because I have equal volumes of each. So when you have equal volumes, your new molarity just becomes half of what you started with, okay? Because you're going to double the volume with the same number of ions. Now, that only works if you're doubling the volume. This process always works when you take the volume times the molarity, you get the millimoles, and then you divide by the total volume. If you want to shortcut it, you can, but listen to me, okay? Ryan Fullerton, I know you. You're going to try and shortcut this process, okay? Don't. You can only have the volume or have the molarity when you double the volume, okay? This is the more correct way to do it every time. That way it eliminates it. All you have to do is take the volume times the molarity, divide by the total volume. This always works, okay? Always works. But if you want to shortcut it, you can only have the volume be half as much when you have equal volumes, okay? That's going to be huge. Now, with that said, now I want to calculate my QSP. So my QSP is going to be my magnesium ion concentration times my hydroxide ion concentration squared. I cannot emphasize this enough. This is what you're going to screw up. You are going to forget to square this value. You mark my words. You're going to forget to do this, okay? All right? Get in that mindset, all right? Words, get into that mindset. You got to square that number because there's a 2 in front of it. So what I'm going to do is that I'm going to take my magnesium ion concentration, which is going to be 0.40, and then I'm going to multiply that by my hydroxide ion concentration, which is going to be 0.3, but then I'm going to square that. Okay, so give me a second. Let me do some calculations here, because I just completely made this problem up. Okay. So I get a QSP of 0.036. Okay, that's my QSP value. Now, at this point, you compare it to the KSP. So the QSP is 0.036. The KSP is this incredibly small number of 1.8 times 10 to the negative 11th. So at this point, this is why I formed a precipitate. Because at this point, Mother Nature's going, oh dear Lord, okay? These concentrations of ions are way, way, way too big to exist as ions. Mother Nature goes, look, y'all, okay, a lot of you are going to have to chill out and sit down. So that would, imagine this, picture this. I walk into a room and let's say my equilibrium value, let's say I'm teaching second graders, God forbid. I walk into a room and my equilibrium value is, let's say, 10. Okay, that's when I'm in equilibrium, right? I can handle 10 kids roaming around in my room. If I have 10 kids, I can deal with that. That's my equilibrium number. Some of you are laughing and going, Berkey, that's way too optimistic. You would flip out if you had 10 second graders roaming around. You're right, but go with the story, okay? Go with the story. You all know me well. So, I know Rachel Meek would be sitting back there going, behind the mask or whatever, Berkey, you would be flipped out, okay? All right, so, but let's just say for the sake of argument, that's 10. Now, I walk into this room. And let's say that I've got 22 little second graders all roaming around. My equilibrium number is 10. Okay, it's like, oh dear Lord. Way, way, way out of equilibrium. Okay, so what that means is that I'm going to make 12 of those little ankle biters sit down. It's like, 12 of you, sit down now. Okay, imagine that I said that to a second grade class. I would be getting emails all night long from parents going, you made Timmy cry. Yeah, I did. Suck it up. Okay. So I would come in and say, 12 of you, sit down now. And then you're like, oh, okay. Because I can only handle 10 of you up moving around. Now, because this is what's happening here. This QSP value is huge. So Mother Nature wants to get back to a KSP value of 1.8 times 10 to the negative 11. So Mother Nature is going to go, wow, okay, y'all are going to have to sit down and make a precipitate, okay? The same thing happens with this classroom, okay? I walk in, there's 12 kids sitting around, it's like, oh dear Lord, no, okay, this is bad. I can only handle 10. Now, visualize this though. Let's say that we had done this calculation and the QSP had actually equaled 1.8 times 10 to the negative 11. Let's play the what if game. If this had actually equaled 1.8 times 10 to the negative 11, that would just mean that the system is in equilibrium. Now, that would be like me walking in and going, hey, my equilibrium number is 10. I walk in, I have 10 kids in the room. Cool, okay? I'm in equilibrium. I'm not going to make a precipitate, okay? I'm good. Now, what you'll see is to actually form a precipitate, your QSP has to be bigger than your KSP by like a factor of 1,000. If it's just slightly above it, then you won't make enough precipitate that it's observable. So if your QSP is quite a bit bigger than your KSP, that's really going to make a precipitate. Now, that would be like me walking in and there's like 11 kids in the room. One of them might sit down, the other one might stand back up. I can live with it. Now, here's the other thing that you need to visualize. This is not a static situation. So once I make that precipitate, because my QSP was so much bigger than my KSP, it isn't a static situation. You always have an exchange of these ions from magnesium going into the solution, magnesium coming back out. Hydroxide going out of the solution, hydroxide coming back in. So this isn't a static situation. These ions are being exchanged all the time. But you're only going to have an equilibrium. So that would be like me walking in. I got 12 kids sitting down. I got 10 of them moving around. Timmy says, hey, I need to go sharpen my pencil. Fine, Timmy, you can get up, okay? But then Susie is going to have to take his place because, again, I've got to be in equilibrium. All right. Now, the cool thing that you can do is that imagine up here in this area up above, and that's why I said you have to focus on what's happening in the solution. So I got some magnesium ions, I got some hydroxide ions. Now, here's the cool thing that you can do. I'm going to add some hydrochloric acid, okay? So I'm going to add some hydrochloric acid, give that a swirl. Now, here's what's happening up above. What's happening up above is that I'm adding hydronium ions. Those hydronium ions are bonding with the hydroxide. Oh, we're making water, okay? So we're decreasing the concentration of the hydroxide ions that are up here. At this point, Mother Nature's going, oh, I still got to maintain equilibrium. So what's happening is that my precipitate, if you notice, is there's a lot less of that precipitate because Mother Nature's going, ooh, those magnesium ions or those hydroxide ion concentrations are dropping. I got to make more. So if I add some more hydrochloric acid to it, okay, I can make that solution go clear. Because what's happened is that Mother Nature says, whoa, if you decrease the concentration of these ions that are up here, Mother Nature still wants to be in equilibrium. So Mother Nature is going to make this stuff to dissolve. So that would be like me sitting here and the bell rings for recess, right? I like my equilibrium to be 10 kids moving around. Bell rings. Kids start to leave. Okay. Some of you that are sitting down, because some of the kids are moving out because they're going out to recess. Like Timmy's left. Susie, get up, take Timmy's spot. So as kids file out of the room, I still want to have 10 kids in the solution. Okay? So now, if I walk in and there's only 8 kids, if my QSP is less than my KSP, I don't have to make anybody sit down. I have room for more. Same thing is going to happen here. So if your QSP is less than or equal to your KSP, you're not going to make it precipitate. Okay. So with all that said, so your assignment is only these 2 problems. Okay? So you're going to write the equation, the net ionic equation between lead-2 nitrate and sodium hydroxide. Okay? So you're just going to start off, okay, PB nitrate, okay? And that's going to be aqueous, which means that they're floating around. And sodium hydroxide, okay? Right, they're floating around. So lead's going to bond with the hydroxide, nitrate's going to form, sodium's going to bond with the nitrate. Look at it and say, wow, am I going to make it precipitate? If you're not sure, go to page 1093, or you can look at your solubility chart, and you could look at this and go, wow, here's lead-2 hydroxide. Where's lead-2 hydroxide? That's not on here. Weird. Okay, take my words for it. They must not list all of them. Lead-2 hydroxide is insoluble. Okay, most hydroxides are insoluble. You can't find a KSP value. This is just odd. Oh, now I remember. That's why I gave you the KSP of lead-2 hydroxide, because it wasn't in the book. Now I remember why I have this problem on here. Because this isn't listed in your book. Trust me, lead-2 hydroxide is your insoluble product. So, now, here's what I want you to pay attention to. I'm going to mix 20 milliliters of this and 30 milliliters of this. Because I'm mixing unequal volumes, I can't have the molarity. So you got to take 20 times 0.1, get that number of millimoles. Take 30 times 0.3, get that, and then divide that by the total volume of 50 to get the concentration after they've been mixed. Now, when you get down to number 5, I was nice on number 5. I got 30 milliliters of silver nitrate and 30 milliliters of sodium carbonate. Now with this one, because I'm mixing equal volumes, you can just have the molarity after it's been mixed. So this is going to be like 0.05, that's going to be 0.1. Now what you have to watch for, because your precipitate is going to be silver carbonate, which is Ag2CO3, so that's a situation where you have to square that silver. So your only assignment, and this is going to be, I got to think this through, today's Monday. You're going to watch this on Tuesday. This assignment is going to be due on Thursday. Okay? All right. So there we go. I hope that kind of made sense. Anyway, peace out, kids. Stay warm. Stay safe.